In this video, we're going to outline the basic approach of Kosaraju's algorithm so that we can dive into it a little bit more, dive into why it works. So first of all, what is Kosaraju's algorithm? It's an algorithm that helps us find the strongly connected components of a graph. Basically, the strongly connected components of a directed graph are the components where, well, two things are in the same strongly connected component if I can get from one to the other and then back again. So for example, I can get from A to C, and I can also get from C to A. So those would be in the same strongly connected component along with B. So I'll go ahead and draw a little bubble there. I can clearly get from D to E and from E back to D. So those seem like they're in the same strongly connected component, but that's actually the whole strongly connected component there. For instance, are C and D in the same strongly connected component? Well, no, because I can get from C to D, but I can't get back from D to C. So the only thing in this strongly connected component is going to be those. F, there's basically, once I go away from F, there's no way back, and once I get to F, I can't get back to where I started. So F is actually its own strongly connected component. And then last but not least, G, H, I, and J are all a strongly connected component here. Okay. So we were able to do that kind of just by looking at this, but how could I find this in practice? So one way, and this is going to be easier to think of with a picture that already has the strongly connected components labeled. First of all, what is this? We kind of have the metagraph. So note, this is the metagraph. Often you'll see a metagraph written as like my vertices A, B, and C are in one node. Then we'll have the vertices D and E in this one, and we have an edge from A, B, C to D, E. And then I'll have going to F, and then going to a node representing the connected component or the strongly connected component G, H, I, J. So if I already have this metagraph kind of in my head, here's a way that I could just kind of explore each strongly connected component one at a time. Is what I could do is I could find a sink strongly connected component. Basically a strongly connected component that's a sink of my metagraph, so there's no edges coming out of it. And then I should be able to explore starting from that sink. Explore starting from a vertex in that sink. So let's take, for instance, I, just because this is a, kind of an interesting component. If I start with I and explore, well, first I'll go to G, and then I'll go to H, and then I guess I'll go back to I, so we've kind of processed that. But remember, I also has this neighbor J, so we'd also explore that and then go back to I. And then at that point, there's no other things to explore. There's no other edges going out of this strongly connected component. So what we did is we got to everything in this sink and nothing else, because it is a strongly connected component. There's a path from I to everything else in this sink, but there's not necessarily a path from I to anything else because it's a sink strongly connected component. There's not any edges coming out of it. So if I explore starting from a vertex in the sink, all I should get to are the vertices in that sink. Okay, so I do that, and then maybe when I'm done with that, let's go ahead and either delete or maybe ignore the vertices in that sink. So maybe I, scratch this graph off. And then maybe I increment some counter that's keeping track of my strongly connected components. And then I go ahead and find a new sink. Maybe something like DE, or even F. F is a sink if I've gotten rid of this guy, because the only edges going out to F went to this strongly connected component. So that's not there anymore. So if I start at F and explore, it's very boring because there's no outgoing edges from F anymore. So you could find a new sink, explore, delete it, increment a counter, find a new sink, etc., etc., etc. And then as you do this, you'll progressively explore each strongly connected component. So that's all well and good, but there was a really big part that we had to do, which was find a sink SCC, or at least find a vertex in. We had to find a vertex in a sink SCC, and that's really hard to do if I don't already know what the SCCs are, what the strongly connected components are. And then I also need to keep being able to find new sinks. So this is, if I don't know what they are already, this is obviously a lot harder. The good news is we're going to talk about how you can make sure you find a vertex that does belong to a sink strongly connected component. We're also going to talk through the reasoning why that approach works. So that's what we're going to do next.